Piotr Dudek from University of Manchester, and he'll be talking on Neuromorphic Vision Sensor which I think he has been working last 20 years?
30, my fourth, yeah, I don't know. Okay, yes, so that's the title. Okay, thank you. I'll start with the motivation for neuromorphic vision, right? And it's making machines see, right? We want computers to see, and we can do amazing things today, right? With computer vision, when I started doing this, you couldn't do stuff you can do today. Object recognition, visual navigation, whatever you wanted. You download stuff from GitHub, your favorite framework, you get your favorite model, you get your data set, you train it, whatever your task is, we can basically solve it, I think. So the problem is solved. That's the end of my talk. Thank you very much. And the questions. Obviously, it's not quite solved, because the way it is solved is by using a massive amount of compute. So if you can afford that, and it is amazing what we can do today. There's no question about it that the stuff we can solve is incredible. If you have enough battery, if you have enough electricity, if you have enough time, if you have enough money and enough data, then you can pretty much do anything. Okay? But the kind of problems that we often apply computer vision to are ones that do not have time, money, data, or battery. So you may want to have your computer vision on agile robots, that have to move fast. They don't have time to send the data to the cloud for analysis. Yet they have to do this on board. They're constrained by the battery power they can have, by the size of the system. Maybe you're building robots again that need to react quickly. Maybe they need to be cheap because they're consumer products. Maybe you don't want to send data to the cloud because you're concerned about the privacy of your data. Maybe again you're doing some very high-speed control loops. So cloud is not a solution, but like in many of these cases, a big GPU is also not a solution because it's too big, too power hungry, too expensive. The tiny things are too slow, right? And whatever people will tell you about tiny ML, the deep networks work because they're large. You can quantize, you can prune, but if you quantize and prune too much, that things stop working. So we don't really have the hardware to run computer vision on robots, and so that's why we want to do something. So what's the problem with the hardware? And the root of the problem is how we do computer vision in a kind of conventional way. We have a camera and image sensor. We send this data to our compute platform, and we're sending lots of data, lots of images down the pipeline. And I mean, often by the time you've sent the video through, you've already consumed too much power or spent too much time that you would want in the application. You might have lost the game when you've already sent the data through. And then you have to process that data. And we know, again, this is something I don't have to explain anymore, is computations are kind of almost free. It's actually moving data around that costs time and energy. So moving data from the sensor to the processor system, moving data within the processor system too. It's a lot of pixels you're dealing with. So your CPU, GPU, memory, AI, whatever you have to move that data, and that costs energy. Okay, so what's the solution? Well, we have a neuromorphic solution, right? Event camera. We've solved the problem because rather than having the images, we are sending events. And that's quite wonderful, except that there's still lots of it's not. This is not the neuromorphic propaganda, if you like. There's still lots of events very often. If your camera is moving, then actually you have to deal with all these events then, right? So yes, it helps. Yes, the camera could be pretty fast, and we certainly do amazing things with this kind of event cameras. But data movement still costs time and energy. CPU, GPU, you're getting into issues because your data is sparse, is irregular, so you cannot really stream it very easily. Your AI accelerators stop working. Your cache doesn't work as it should because you have irregular memory access. people who try to process spiking data when you have a lot of spikes and try to do things quickly know that you cannot really do this easily. So spiking neural nets to the rescue, right? Maybe we can have spiking neural nets that do this, but we don't actually seem to be super successful in doing spiking neural nets for vision. Yeah, it's interesting, and we're doing great efforts, but in practice, things don't really work that well. Coming up with event-native computer vision algorithms, right? There's a lot of probably more effective work is that. A lot of people are working with really nice algorithms, how we use events to do computer vision in a different way. Great stuff. Often people resort to recreating frames because we really know how to do computer vision on the frame. So once you got the data out of the event camera, you pull it back together into an event frame or some clever event frame like Chiara was kind of doing. And then you apply conventional computer vision to it. So we are kind of back to square one, moving data and trying to compute with that. But the question really is why we are so kind of hung up on this one type of event that event camera are producing. This is kind of on-off events with the pixel intensity change. You generate still, you may generate quite a lot of those events, especially on a moving platform. Another question is it even neuromorphic? I mean, is it really a biological kind of biologically plausible retina? So that's another kind of question, because we just say, it's neuromorphic, it's biology, it works like that. It really doesn't, right? It's nice abstract event camera, it's not neuromorphic. But then, should it be? I mean, who cares whether it's biologically plausible or not, as long as it works? So, good question. But I think the question is, can we do better? Is it like the best event camera you can build? And the real idea for doing this kind of computation in the camera, in the sensor, is that you can push that computation into the sensor. You don't have to move the data. You do something in the sensor so that you something that allows your data to be sparsified. You have much less data. It's compressed. It's more meaningful, and so it's very easy to process on the back end. I think this is the philosophy. This is why we started building these neuromorphic cameras. And of course, the inspiration is the biology, right? And we know that sensing, processing, behavior, it's all part of one loop, right? Brains are there to take the sensory data and process it and produce the motor responses and help animal to survive like that. And retinas are brains, right? Retina is not an image sensor. It's a processor of visual information. It's a part of the brain. It develops from the brain tissue, and if you look inside, and there's a lot of stuff going on, right? There are photoreceptor cells. There is a lot of neural circuitry in there, and it's very complex. There are this plexiform layers, the stratified layers. There's a lot of different connectivity, a lot of different neural circuits, a lot of different cell types, and distinct processing circuits. And people say there's 20 different types of encodings that are produced by the ganglion channels. So it's not just on and off, right? There are the centers surround filters, and they're kind of sustained and transient responses. You have different temporal scales, spatial scales, and people, even say, there's a lot of more complex things that go on. There are some ganglion cells that respond to motion direction. Maybe you are doing things like global motion suppression right in the retina, motion against background, looming, right? If a rat can recognize the looming bird in the retina, so it can run away even before the cortex gets the signal that a predator is approaching. So eyes are computing, and I'm not the one to tell you what they do, because there'll be better people to do it, but you can read interesting papers about what actually comes out of the retina. And it's a lot of really complicated things, and not fully understood, I'm sure yet, but certainly a lot more than just temporal contrast events, right? There's this really nice review by Golischmeister where he talks about all these different types of neural circuitry with a sentence here that says retina solves a diverse set of specific tasks and provides results explicitly downstream to brain. And that really, there is a lot of complexity in there. Okay, and it kind of when the neuromorphic computing started, we started building sensors and silicon retinas. This is the Misha Mahawal's paper, and trying to replicate that biological complexity in some way. And this Kwabena's paper, kind of more complex, many types of ganglion channels here. This is very recent, by I think everybody of the authors is in this room, trying to build a more complex silicon retinas. But there's then also another aspect to how far we should be going with biomimicry, right? It's still engineering. I mean, neuromorphic engineering is not about just replicate what the brain does, what biology does, but somehow being inspired by that, try to engineer systems that do things well and maybe even outperform biology. And so this is really our most successful approach to that, the DVS paper, right, where now you have this really fabulously performing cameras, very high quality and doing things really well, and a lot of people are doing great things with them. And I mean, don't get me wrong. I think it's really fantastic things that we managed to do with this. Okay, but we could be doing other things. Yeah, okay. Can there be a more sophisticated silicon retina? You have this retina that outputs meaningful data. What that meaningful data you would want it to be? Yeah, what kind of events or what kind of information your retina is sending to the brain? You may want to do things like spatiotemporal filters and motion change of direction, maybe optic flow, the kind of things that we hypothesize are happening in the retinas. But maybe also other more kind of engineered things, like the backgrounds. Maybe your retina can do semantic segmentation or extract key points for the SLAM system, do object recognition on the retina. Who knows? Okay, we can dream. We can do more than the biological retinas do. The idea is, we do compute here rather, and then send something which is already meaningful. And if you know what you're trying to do, you can optimize this sensing for your application. So you can build a chip that does optic flow, or build a chip that does convolutions, and people are doing these things as well, right? Or you could try to build a universal retina, a chip that can do it all. Okay, general purpose retina system that computes in the sensor and computes anything. And if you have one, then you basically program it. You write a program and say, I want it to do this, I want it to do that. That's really great, no? So if you do this, we know how to build programmable system where we build computers, we build processors. That's what we've been always building. And so if you want to have a chip that does it all, you could put a pixel array, you could put a processor next to it. You can buy Sony IMX500 that does exactly this, right? It's all in one single package. It's really nice, efficient, quick. But in a way, this is still the same, right? It's miniature, but it's still the sensor sending data to the processor. What you really want is to have this kind of processing and sensing all together, like what we do in the eye. So this kind of embedding of processors and sensors is what I've been working on for, she said, 30 years now. And this is what we're trying to build. Okay, so you have this camera. The light goes through the lens onto the sensor, and what you have in the sensor is this processing and sensing circuitry all enmeshed together, where you have photodetectors, you have processing circuitry, but you want it to be programmable. So you want to sense the light and output something interesting out of your system, and you want to decide what it will be later. You want to write a program to do one thing, or maybe second program to do something else, on a third to do something still different. So you really want a programmable processor, okay? And if you want to do this like in this massively parallel way, like biology does, then you ideally would want to have a microprocessor in every pixel, so that you have this big array of microprocessors that process visual data right there at the point of capture. So I'm saying you have to put a microprocessor into a pixel, and that may seem a little crazy, and it probably was crazy 30 years ago, but it isn't really that crazy today. Having a microprocessor that is so tiny that fits into a pixel isn't quite crazy. This is my history of image sensing, and what can we put into a pixel? Like on a smartphone, you have pixels which are less than a micron. Okay, they're really tiny. They're pushing the resolution. If you're looking for like a machine vision camera, you probably have pixels maybe 3 micron, 4 micron, maybe up to 10 micron on the side. Bigger pixels if it's a global shutter camera or something like this. In other sensors, if it's an infrared or a spot imager, you actually go maybe 20 micron for a pixel size. But you can put quite a few transistors in that area. The first sensors didn't have any transistors. They were CCD devices, basically buckets that you collect the charge in. The APS, the kind of traditional image sensor, has 3 or 4 transistors in a pixel, a reset and readout circuitry. A global shutter sensor has to sample all the data at the same time, so it has a few transistors to store the kind of entire frame at the same time, rather than doing it row by row. That leads to artifacts. So maybe 10 transistors or something like that. People are talking now about digital, DVS is about maybe 20 to 50 transistors. If you do that, you can do something quite clever in a pixel, detect the contrast change, send out the events. Very nice. People trying to build digital pixel sensors which have an A to D converters in pixels. Maybe about 100 transistors. You can have an A to D converter inside every pixel to do a very fast conversion, save it. So you see where this is going, right? I mean, it's a few more transistors. We can have a microprocessor in the pixel. Why not? And how big a processor needs to be? Processors actually don't have to be huge, but let's look at the densities of the devices that we have today. So, and kind of old technology, the one that the SCAP systems are built on is 180 nanometer CMOS, is about 30,000 transistors per millimeter square. So in a 10 by 10 micron is kind of pixel, but it's not like crazy large. It's about 30 transistors in that area. So the kind of DVS type of circuits you can build. In something like 28 nanometers, which is a really cheap kind of run-of-the-mill technology today, it's about 12,000 transistors per millimeter square. So about 1,000, you can fit about 1,000 transistors in a 10 micron by 10 micron pixel. If you go to something more state-of-the-art, you can fit about 10,000 transistors in a 10 by 10 micron. That's quite a lot of transistors in this area. How many transistors you need to build a processor? An ARM processor is maybe about 30,000 transistors. It's not caches or anything. It's just a data path. Yeah. My favorite processor, 8-bit Zilog Z80, about 8,000 transistors. The first Intel 4004, right? It was a 4-bit transistor. It's about 2,000. Processor about 2,000. So yeah, obviously you reduce the size of a data path, there'll be fewer transistors needed. In a 1-bit data path, in a bit serial transistor, you probably need about 1,000 transistors to build a microprocessor. There's actually a guy somewhere, I should reference this, who builds RISC-V data paths at about 1,000 transistors in a bit serial, and they actually execute a RISC-V instruction set. So we started building these bit serial processors and fit them into pixels. This is one of the chips called ASPA3. It has a fully bit serial processor. There's about 600 transistors in a processor and 1 bit ADC, because you have a pixel and you need an analog pixel in ADC. That was 180 nanometer CMOS, about 50 by 50 microns, so still quite large, but not crazy large. And this is 180 nanometer CMOS. But now we can think also, can you do better than 1 bit? Can you build a processor more compact, more efficient than bit serial? And we had a really good introduction to analog computing, so there is still way to go. Question?
So in the PE, you have 588 transistors per processing element. So what's there in the processing element? Sorry? What's there in the processing element?
The processing element is a tiny microprocessor. It has a memory, ALU, it can run programs.
Yeah, in this case, is it like just, what type of Mac does it have?
It has a kind of simple instruction set. You can move the data from a register to register. You can do logic operations on data. If you want to do addition, you do kind of bit serial addition. You have a 1-bit adder. I mean, here we had a like 1-bit adder as a basic ALU.
What's about memory?
So yeah, so there is so this I think there was 64 bits of memory in a processor.
So they have their own code memory?
No, this is when you build things like this for image processing, you want to build a SIMD array because you do the same thing in every pixel. So actually, you only need one controller, one program memory, and you just issue all the instructions. So it's somewhere on the side you have a controller that runs a program and distributes my kind of instruction codes to processors. Yeah, so this is really just a data path. Like when I call it microprocessor, I'm calling microprocessor because it's
Predicate bits for the operations, so that you can do different operations in different.
You typically can do something, you can sort of disable certain processors in the array to do something else on them while the others are asleep. So there's certain flexibility there. But it's a kind of it's a simple control scheme. It's a traditional kind of vector processor like architecture.
Matrix processor.
Huh?
Matrix processor.
Yeah, that's right. It's a matrix processor. Okay, so can you build a processor with even more efficient data path, and you can build an analog data path in the microprocessor. So it's a kind of different type of analog computing. It's actually still computing with a processor that has this architecture of an ALU, data path, instruction set. It runs software programs, but actually the data path of the processor is analog. So you can have analog ALU, you have analog registers, and as with all analog compute, you can get a really high efficiency, small circuit area, low power, because you do these things in analog. And even better, you don't need A to D converter now because you just take the data from the pixel and you start computing with that straight away. And I mean, typically we build this as a mixed signal processor because you still want some digital compute. So you have this you have analog compute, you have digital compute, you put it all together. So this is this is our analog or mixed signal processor, and this is the chip, the SCAM5 chip that I have here, a few of them, and we built it. I mean, this chip has been built like over 10 years ago now. It's a 256 processor array. There's a 30 by 30 micron pixel, so a bit smaller than on the bit serial processor. It can run, runs at a pretty slow clock. Runs at about 500 gigaops per watt. Okay. Now, you can build it, and this is in 180 nanometer CMOS. So again, an old technology. If you do like a multiply, accumulate, accelerator, something like you can really parallelize very easily, then you can get teraops per watt probably in this technology. If you build a general purpose microprocessor, that actually isn't too bad a number. Okay. If you get an ARM, like a programmable processor, ARM M0. About 12 gigaops per watt. NVIDIA Tegra, much more advanced technology, that's about 100 gigaops per watt in terms of like ops you have for executing programs. And we can argue what is a gigaop, and also I think it's not really how big your gigaops are, but what you do with them that matters. But it gives you a kind of ballpark idea of this is really high performing processor in a really old technology. But then, okay, we can take it a lot further today. Yeah, we can stack it. So this is all like a planar. This is okay. Photodiode is here. Most of the pixel is actually the processor, which is kind of wasteful from the point of view of collecting light. But today you can get 3D technologies that allow you to stack the sensor tier and processor tier, and you can use more advanced technologies. The Prophecy, the Sony Prophecy chip has a 65 nanometer kind of sensor tier, or a 90 nanometer and 65 nanometer processor tier. So it's a much more advanced. This is something that was a couple years ago at ISSCC where they use again the sensing tier here and there is an ADC converter under each pixel. So actually this kind of stacking allows you to do things like A to D conversion in a pixel. And this never ends, right? When it starts, it's like with the shaving blades. There was 2, then 3, then 4, then 5. So we can expect, and people are building 3 tiers already. So there was a paper at see from OmniVision. It's actually an event camera with a color sensor at the top, and a patch of 4x4 pixels connected to the DVS type of circuit. And then on the third tier, you have some additional logic circuitry. So it's, you can really start dreaming about putting quite a lot of circuitry under your pixels. And that's really great. I promised to dig out some old stuff. So we actually tried to build the 3D chips like that maybe 10, 15 years ago. Not entirely successfully, I have to say. We were probably a bit too early. Today you can do this. Yeah, Sony Prophecy is a 3D stack chip. ST Microelectronics has that technology as well. Actually, the new Prophecy chips, the Gen 320, whatever they call it, are in this technology. It's a 6540 stack. The OmniVision, again, this is a 3-tier stack. So this is now industry standard. It's not something crazy, and really enabling technology for building silicon retinas. So this is the architecture of the chip, right? This is still quite a small resolution. I mean, this is an academic project, but you can have the SIMD array. Each pixel is a microprocessor, so it's super flexible. You have things like event-based readouts. So once you've computed, on your matrices and reduce your data to a sparse matrix. I mean, maybe you're computing what pixels have changed, and only a few of them have changed. Maybe you do something more complex and see where are the corners in my image, and I only have 50 corners. Then you can turn this data into events. Rather than scanning and outputting the images, you output them as event stream. But those events now are quite loaded, right? It's not just an on and off for a sensor. You can have an event that represents anything. Because you decide in your program what kind of events you're producing. And as I said, we built this chip more than 10 years ago. Most of the last 10 years we spent playing with it, and we still haven't finished. So building a whole kind of software ecosystem so that you can actually start using it and start writing the programs, building the hardware systems, and then trying to use it. Well, I have to say there is a later version. There is SCAMP 7, so it's in the. I have one here as well. It's with a smaller camera. It's pretty much like SCAMP 5 actually in terms of what is on the chip. It's not different. People wanted a bit more memory, so there is now 22 bits of memory, digital plus still 6 analog. There are some kind of additional improvements, and maybe a lot more of the peripheral electronics was integrated into the chip, just to make it a little bit more compact as a system. Okay, so that's kind of what we've built, and now you have the chip that you can do anything. You have retina that can do anything. So now you really have to ask a question. So now what? What should it actually be doing, right? And that's really the research question. So we have the retina. We want to send some kind of meaningful data between that and the rest of the processing system. But what that is? Yeah, if it's not on-off events, what kind of events you're sending? You can build maybe, and there's kind of various ways in which you can do this. Yeah, you can think maybe I'm building an enhanced sensor. Maybe I built just a different kind of sensor. Maybe I use this ability to compute to improve the dynamic range of my sensing, or deblur the images, do the motion deblur, or maybe compute optic flow, or maybe depth. There, I'll show you how you can do things like that. So you can build this enhanced sensor. Maybe you go the other way around and say, actually, because I have this processing array already there, maybe I'll do my entire application in here, and I don't have to do anything else. Maybe that meaningful data will be just a result of my computation. Maybe I'm trying to, find a target, and I just send the location of the target as the output of the sensor. And the whole thing is solved on the sensor itself. Or, and I think this is kind of the bigger question and a more practical thing, you do something on the sensor. You output some kind of feature or compressed data or encoded data. You produce something that is most useful for the application, but you still have the kind of flexibility then to do something a lot more complex on the off-sensor processor. So that kind of partitioning of the visual pipeline becomes a question. And the biology did some kind of partitioning for that. Yeah, put some kind of filters in the retina and put some kind of processing in the brain, perhaps optimizing, what is being sent there. But again, here we have a freedom to think what the optic nerve should carry.
So biology also has that bandwidth problem, right? The optic nerve.
That's right.
So I had to.
So it has to be doing something like that.
Communicating over distance, so it might well have gotten it reasonably right.
That's right. That's right.
What are the limitations for interactions between pixels?
Yeah, so okay, I maybe wasn't very clear. The pixels can talk to the neighbors. So you can fetch data from a neighbor. Yeah, but I mean, you can ask for the third neighbor and they'll pass the data to you. So you can basically build networks which are communicate processes, yeah? Okay, so for the rest of the talk, I'll just show you a few things that we've been doing with this, with the sensor to give you a flavor of what kind of things the retina can do now. This is just that first thing. Can we just use it to improve sensing? One thing that DVS type of sensors are really good at is a high dynamic range. It's a high sensitivity, but also high dynamic range. You can, if you just use a frame, capture a frame at a short exposure, you can see the bright stuff, but you cannot see the things that is you know, a bit darker. If you expose for a bit longer, you see the things that were there in the dark, but you then overexpose, yeah, oversaturate. But you can do a really nice sort of you can actually capture lots of, because now we're not sending these images out of the sensor. You can decide, you can capture many exposures in the sensor itself. You can actually, each pixel can decide for how long it wants to expose, depending on what neighborhood it is in. And if you get it right, you can get this really very high dynamic range images. It's 120 dB, is pretty much like what DVS does, which is in this case tone mapped, so that you kind of equalize this, which is more like what Retina's kind of filters are doing in first layers. And we compute all that as we integrate the frame, so we're actually not wasting any time. By the time you gathered enough light for the darkest things that you want to see, you also finish with your computations of a tone map image, and you can just output that. So you are kind of only bandwidth limited by how dark are the things that you want to see. But you can do this in other ways too. This is a paper where we simply were integrating to saturation, and when you reach that, you reset it again and integrate to saturation, and again you can count how many times you did it, and you can get a high dynamic range like that. And there's probably many other different strategies you can try. You're free to. It's all software, right? So you just write a program saying I want to do image acquisition in this or the other way.
One question before, you said that they share their memory, so their instruction memory is shared. How can then different processors do different things, for example, in this long and short-term exposure example?
Okay, so there is a certain level of autonomy of each processor. Each processor can either respond to the instructions that it receives from the controller or not. It's like masking in, you know, if you mask certain instructions, if you write vectorized code in NumPy, and you use a mask to not change a state in certain bits of your array. So that's kind of how it works, yeah.
Stored in this kind of very small local register.
That's right. So there's a local memory that basically tells you, okay, at this point I'm masked, I'm not responding to instructions. And so in that way, each pixel can basically decide, okay, maybe now is a reset time, but I will not be resetting because I'm happy what I'm doing. So you can those processors can do different things, but they cannot follow the single instruction stream and just either do things or not. Okay, so this is another kind of thing that you would not probably do in a conventional camera because you have to process quite a lot of frames to do this. It's depth from focus. What you capture images as you change the focus of the lens. So these things nearby come into focus. As that lens changes focus, things further and further. And you can quite easily write a program that estimates local contrast, maximizes that contrast. And if you do that sweep, the time at which your contrast is at maximum basically tells you something about the depth of the object at that location. And we put a liquid lens there. They can change the focus really quickly. At 60 hertz, it goes from near to far focus. And during that sweep, we sample the images, do the analysis, and so at the end, we have a depth map, which is computed, you know, at 60 hertz. We actually, to do this, we have to process during that sweep. So the processing is what I say here, 7,000 frames a second. Yeah, it'd be kind of crazy to try to do this with a camera that outputs 7,000 frames per second just to compute this. Very often impossible, but very easy to do when your data is there at the sensor. Johannes.
I also included SPAT diodes for this application. So have you also included the silicon photo avalanche diodes, SPATs, for this application?
Yeah, you could think about doing this with SPATs. I mean, we've never done that, but I mean, it's definitely something you would think about, yeah. And then do your photon counting in a processor, and then do something again with that information.
But the SPAT is not so sensitive to crosstalk from the digital parts, well.
It's definitely, yeah. In a way, this is kind of sensing modality agnostic, right? This approach. You could imagine all sorts of sensors, as long as they are arrays and you want to compute fast. Okay, this is a little video that's showing that. It's probably it's less than 60 FPS in this case, but it's a kind of live video that compute. There's a depth out of a single camera with an oscillating focus. Okay, there's maybe some simpler things, but you know, this is optic flow. People often want to compute flow. You can just compute the flow in the sensor, write a little program, just using actually block matching algorithm. It's again, block matching is usually not very efficient, and people do flow in other ways. But with a processor array, it's actually quite efficient to do block matching algorithm, just by checking all the locations and maximizing the one frame to another similarity. So okay, so you can compute this optic flow, and then you can just output it. But probably you actually just want to do this as a first stage of your processing, and then still do something more with it. You have a flow map, now you can do something else with it. Okay, here is a corner detector. So we implement a little program for a fast 16 corner detector, which basically means you take this pixel and you compare its magnitude with all the pixels around it, and there are some rules on whether that comparisons are positive and negative that tells you are a corner or not. It's a nice algorithm, relatively simple. You can run this at about 480. Well, we're running here 480 frames per second, tracking all these corners. Well, we're not tracking; we're just outputting the corner locations. But actually, you don't need a gray level image. You can only output only the corners, because who cares? If you're doing SLAM or something, like you want to know how you're moving, you have all the information here. That can run at about 2,000 frames a second, right? So 2,000 FPS. It's really hard to get the images at 2,000 FPS out of the sensor. These are events, so we do this as an event readout. So each event means there is a corner, and we read out those events, a few hundred maybe per frame. Okay, this is the new one. Even more exciting. This actually is not only better, but also faster. And this chooses which corners to track and labels them as well. So it's really very stable. It's kind of when it loses a corner, it picks up another one. Again, I'm showing here both kind of the gray level frame from the SCAMP and something recorded with a phone camera, just to show you how rubbish things are if you don't have a global shutter. You know, it's all kind of wiggly and blurry. But actually, this grayscale image is also blurry, but the actual corners are being followed. Yeah. So 3,000 FPS for the full corner detector. Very sparse data coming out of the sensors, event that tell you these are the corners. Okay, you can do, but this is some kind of odometry thing where you just want to figure out the global motion of the camera. There are balls here from a Vicon tracker, so we try to have a ground truth and then compare it. So one of the traces is what camera, like I think the light blue is what we do from the inside out tracking, and the dark blue is from the Vicon in the X direction, and here is in a Y direction. And we kind of get a pretty much good estimate of the ego motion just by doing the computations inside. And actually, the way that we compute that is that we from time to time we capture a keyframe, and then we just check for alignment with that keyframe on your next frame. And this kind of shows you how this kind of, this is back aligned to the same coordinates as the keyframe. So you see, as the camera is moving, these things kind of try to match, and it's a global match in this case.
So you're storing this keyframe in the digital bits you have per pixel?
That's right. So I think we're doing something here like a high dynamic range edge detection first, then we store the keyframe, and then we compare with we do the same for the new frame, and then if it's go far away, then we store a new keyframe. Okay? And here is some kind of experiment where we walk around campus and try to estimate the motion of the camera based purely on vision. And
can you explain better this comparison thing, because it cannot happen on pixel level because you cannot just compare one pixel.
So this it's a pixel level comparison. So basically, okay, what we do is we capture a keyframe, you capture the new frame, and you hypothesize how it fits, how much you have to move the thing, and you kind of know where you were previously. So you only have to look around the previous thing, and actually we can do translation, rotation, and zooming. Okay. And each pixel then compares itself from current frame and the new frame, which is transformed. And then you sum all the pixels together to give you a global measure of how good that fit is. But I mean, you can come up with other maybe better strategies for that, but that's the one we used. Okay, here's a key tracker. It's again something that your retina here does everything and outputs basically the coordinate of what it estimates the gaze location is. So we extract the pupil and we kind of look at its shape and location, and from that we output two numbers basically. Each frame outputs two numbers, which are XY coordinates, which are uncalibrated, and then we calibrate that with a lookup table in post-processing. And so in this experiment, what we have is the red cross is a cue for the user, just where they're supposed to look. The blob is a Tobii commercial eye tracker to see how good we are doing, and the blue circle is our estimate of where the user is looking, and it's kind of it's kind of in line with the commercial eye tracker, but we do this at 10 kilohertz. Yeah, so we can actually output a new gaze location with, and not only that, also with 0.1 millisecond latency, right? So it's not only we can process fast, but we process this instantly. Like you capture the image, you decide where you're looking at, and that takes 0.1 millisecond. And you only output 2 bytes per frame. Yeah, so it's fast because you can only,
Are you able to get microsaccades with this?
Yeah, we have not looked at it, but it'd be interesting. Yeah, we could certainly look at microsaccades at this resolution, at this temporal resolution. Yeah. I don't know whether you can see microsaccades in this data, but. Yeah. So here again, this runs slower actually because we outputting a gray level image as well, so that you can see what's going on. But this probably only runs at I don't know 120 hertz or something in this particular application. If you switch off this gray level image display, then you can run at a much higher. And we actually run it at those speeds. You need a bit of light, and especially with a SCAMP system which has a tiny sensor and it's not really that good at gathering light. Maybe this is not ready yet for deployment because you need quite a lot of light.
But if you did that as a product, you use that chip solution, right?
Exactly. So that's right. And then like 10 kilohertz, it is very doable. I mean, there's enough light from an infrared illuminator to do this at that speed. Okay, we are playing with robots. Sorry, I just go around to see if it will play the videos. Okay, so we put the camera, the chip on the quad rotor. So here, what it's doing is this is what the chip sees. This is actually a simulation. It tells you what it does. It detects all the gates. It's like a drone racing scenario. Yeah. So it detects the gates and outputs basically the size and the orientation of the gate. So all that is computed in the retina, and that then goes. So there are basically 4 bytes per frame that you're sending out again. That goes to the flight controller that is already on the robot, and you fly around. So again, there's a paper on this somewhere. Here is again, we only outputting, I think, 2 bytes per frame. The idea is to detect certain shapes as the gates, and the car has to do a slalom to go through these gates. It's also quite funny, right? Because if you look at this, it kind of looks not that fast. It's pretty slow. But the first point of view, it's actually pretty fast. Okay. And then people always ask, can you do neural networks with it? So we run some neural network algorithm again on the retina. This is actually an older paper where we implement some kind of 2-layer neural network trained on MNIST. So it all runs on the sensor. The output from the sensor is basically 10 numbers. So these are now the event, if you like, is 10 numbers giving you the probability of the class. And it runs the MNIST classification. We actually have a much niftier object classification now. So that only worked for 1 single digit. We can do these things in parallel now for multiple objects doing classification. So here the event is the bounding box and the class. So that's your event. So we're outputting here 4 or 5 events per frame. The event is the whole result of the computation. Yeah.
How would you rate the efficiency of deploying a neural network on that? Because in a neural network you would have a lot of crosstalk between all the pixels, I guess, if you apply this kind of.
Well, yeah, they can. I mean, things like this. I mean, there's we're implementing actually now a much deeper networks as well. We're implementing a 20-layer ResNet, but everything is a 3x3 convolution. So actually, the pixels don't need to talk too much to each other.
But then in the later layers, you will need to then combine the results.
Yeah, you need to save 1 layer, okay. Then you calculate a few more. You discard as you combine, and then you kind of put that one forward, discard everything else, and go on. It's not like super flexible. You cannot just pull out the network you have in TensorFlow and map it on it. There are restrictions on what kind of networks you can implement. Yeah, you have to work within the constraints of hardware. There's very little memory in each pixel, so you have to think how to do this. But I'm quite amazed that it's not me who wrote this algorithm. I'm quite amazed that they can do this.
But that's my question would be, is it more efficient to do it with this system, or would it maybe be more efficient to take the data out and do it on an external?
It's also a good question, and I think neural nets aren't really the best use case for this. This is actually done by a startup company, so we have a startup company now trying to commercialize this. But everybody asks, can you do neural nets? So they did it. But yeah, whether I think there are more effective ways you can. I think there is merit in computing. Maybe if you want to do something more complex, computing a few layers of a neural net initially on the sensor, where the data is still very localized. Once you start max pooling, once you start crossing over the filters, and you lose the topology of the network, then it's not worth to kind of pushing on with doing this with the pixel processor array. Yeah.
This would be useful for recurrent system, right? Because you can easily build the dynamics.
Yeah. So it's.
I think that's what we are thinking to try, right? LMU or something.
Yeah. I'll show you some other things that we do that kind of along these lines. But if you want to do something like, okay, maybe face or gaze detection or something like this. I mean, here there's also like a detector when the person blinks that it also again. So these are all like a pretend applications. Yeah, maybe it's a driver monitoring system or something like this. Here is a detection of hand gestures. Actually, this is kind of a bit more interesting. So I'll show you how it works later. Or doing some kind of, this is again done entirely on sensor. There's some kind of control area. When people walk into the area, they get detected. The events actually are those bounding boxes. There are people walking there, and there are objects that are new in the scene that weren't there before, but they are not moving, which potentially maybe is, this could be a loiter, it could be an object that is being left, and so on. But everything runs in the camera, right? You don't do wireless transmission of the data. It's really low power in this case. So you can imagine deploying this in various kind of more practical solutions. And this is really more like almost entire applications on the sensor. I wanted to show you how the gesture detection works, because that's more along the lines of what we should do on sensor and what we should do off sensor. So actually what we do on sensor is background subtraction, motion detection, some kind of, so that to get kind of pretty clear image of the foreground. And then we extract oriented edges. And we produce like a sparsified set of events that corresponds to oriented edges, okay? So there's, each dot here would be a single event that comes out of the sensor, and the color is the type of event which is either horizontal, vertical, kind of positive and negative. So that is what comes out of the sensor, and then the back end is a neural network classifier that works with this data to then classify what is the actual object. So that's the kind of partitioning of the application between what is quite efficiently done on the sensor and then a back end which is relatively simple because you've really reduced the data to this very, very sparse set of events. That's another thing that we did along these lines, which is now here we're trying to do a robot navigation. So there's a car that kind of is a driving car. And we compute a bunch of different things that we know how to compute. So it's very much an engineered feature set. But we can compute like a flow or frame differencing, really, glorified frame differencing here. We can compute low-pass filter on it. We can calculate those fast corners. So we just computed a bunch of those things. And we pulled them in receptive fields so that there's actually only 10 receptive fields here. So we have an output of like 10 neurons here, which are like emotion neurons. And then there is 10 neurons here, which are like intensity neurons. And there are 10 neurons here, which are like corner neurons. And these are other types of corners. Ones are corners that are always there, ones are corners that are moving. So and this comes out of the sensor. So you have now 40 bytes of data coming out of the sensor, and then you with it. So what we are training is we're training this on the data that comes out of the ultrasonic proximity sensors to estimate the distance to the nearest object, okay? So now we extracted something quite complex, which we don't know quite what, out of the visual system, and we trained this inputs on the outputs, which is a distance to the nearest object. And we drive it around and to collect the data and then train it, and then so we have these ultrasonic sensors, and then we then switch off those proximity sensors and say, can the robot now navigate as if it had, I mean, it's kind of a stupid thing to do, but it's an exercise. Can the robot navigate now purely based on vision and estimate distance to the objects? And you run the little robot, and it kind of figured out from this very, arbitrary set of vision features that it computes. It kind of figured out where things are so that it doesn't bump into things. And sometimes it bumps into things, but here we go. But it's kind of interesting, and that's I think that's the kind of most interesting thing, right? You maybe do something on the sensor, maybe you don't know quite why, but you can still figure out later that it's useful. Here is something that we did, and then can you actually, rather than making arbitrary encodings, can you train those encodings? So can you train the entire system end to end so that you're not just compute arbitrary features, but you compute something that you may want? And we took this to the problem of coded exposure. I think many people here are familiar with this. If every pixel here exposes for slightly different time, so like if you capture one frame, that all the pixels are capturing light in synchrony. But if you shift the time at which they are capturing between the pixels, and there are some priors. I mean, there is some spatial consistency in the images anyway, so you kind of capture both spatial and temporal information by doing this. And so you can produce this encoded frame where each pixel has a slightly different time slot that it integrates for. And from that frame, you can quite nicely reconstruct multiple frames which have both spatial and temporal information. Okay, so that's a kind of known thing. The question here was, can we now figure out what kind of encodings we should use, what those time slots should be for the individual pixels? And the answer would be, let's just train it. So we trained the whole network, starting with the high-speed video images to basically encode them and then reconstruct them. And these are the results. So this is a single frame that comes out of the SCAM box. And this is what you can reconstruct from that frame with the decoder. Yeah. So and it's an end-to-end trained thing. Again, here we will capture this frame, and from that we can reconstruct something else. So you can capture the 30 FPS video with those encodings and decode from it 480 FPS video. I mean, it's quite an interesting thing to do. And we also kind of train this for high dynamic range sensing as well. And this is the last thing I will show, which is kind of this sort of framework now. That I think is a really interesting thing. So you can build some kind of encoder, which could be quite interesting. Here we put some kind of CNN front end. So this is actually only one layer. You can imagine maybe several layers of a CNN, and then some kind of recurrent network. Here we use a kind of version of a gated recurrent unit. And that all runs inside the pixels. So it produces some kind of encoding, and it's also kind of being max pooled. Which you're sending now over, you're trying to optimize the bandwidth between the sensor and then the rest of the system. And from this data that's been encoded, you try to decode something, but actually, I mean, rather than decode back the images, you solve a task, right? So here the task was, you look at the mouth of a person and you determine what they said. Yeah, so there's some data set somewhere like that. So you can train it now end to end by training the encoder together with the decoder, and you can put the constraints on the bandwidth by doing some regularization during training. And actually, again, this is only preliminary work. I think there's a lot more that you can extract out of approach like that. But so here again, this is the whole thing implemented on the sensor with the encoder implemented and then a decoder. And so that was the last year paper. But I think there's really a lot more that you can do with the system of that sort. And that's kind of it. I just summarized computing pixels, right? You have this fully programmable sensor. It really is very efficient in terms of power consumption, speed. It's really, what we have now is far from what can be really made in today's technologies. And this is really your research question. What the retina should be doing, right? Is it end result? Is it extracted features, or is it some kind of compressed encoded information? How those encodings should work? Can we learn something about biology by looking at the kind of system? Why biology has developed this kind of encodings? It's a nice tool for prototyping maybe future neuromorphic sensors. I'd say it's more neuromorphic, even though it's a microprocessor array. I think these days microprocessor arrays are neuromorphic. Nobody worries about it anymore. And I think it's more of a retina than a DVS, because it does actually a lot more in the retina. The end.